You know, it sounds like something straight out of science fiction, a material that can just change color right on command, but it's very, very real. And today we're going to pull back the curtain on the absolutely bizarre and fascinating physics that makes it all work.
So let's really think about this for a second. How can a window, a totally clear pane of glass, suddenly go dark? And not just dark, but also block out heat when you tell it to. The tech is already here, but the deep science behind why it works has kind of been a puzzle until now.
And believe me, this isn't just about making some cool windows for fancy buildings. We're talking about materials called electrochromic oxides. These things are the key to super efficient buildings, next-gen displays, even high-tech camouflage. So cracking this code isn't just an academic exercise, it's a really big deal for future technology.
Okay, so the whole process gets started with something called electrochemical intercalation. Yeah, I know, it's a mouthful. But all it really means is we're injecting a bunch of tiny charged particles, ions and electrons, into the material. But that one simple action is what triggers this whole cascade of weirdness.
Because here's the secret. The real culprit behind this color-changing magic isn't an ordinary particle, like an electron. No, it's something much stranger, a thing called a quasiparticle. And its name is the polaron. This is the main character in our story today.
All right, so what in the world is a polaron? You're probably not going to find this in your old high school physics book, but trust me, it's a totally fundamental idea if you want to understand how electrons really behave when they're moving around inside a material.
So here's the textbook definition. The key thing to get here is that a polaron isn't just an electron. It's the electron plus the mess it makes in the atomic crystal around it. It's like the electron creates its own personal little force field, and the two of them move around together as one single package. This image does a great job of showing what's happening. See that blue sphere in the middle? That's our electron, moving through the crystal. As it goes, its negative charge starts yanking on the positive bits of the atoms and pushing away the negative bits. This creates a ripple, a distortion, that literally follows the electron around like a shadow. That distortion has a name. It's called a phonon cloud.
And just so you know, this isn't some brand new, wacky idea. The concept goes all the way back to 1933, proposed by the legendary physicist Lev Landau. It got its name in the 40s, and just a few years ago, scientists found proof of a proton polaron. So this whole idea is about as solid as it gets.
So, we've got this electron dragging its own little distortion field around, this phonon cloud. What's the big deal? Well, it turns out this cloud isn't just tagging along for the ride. It fundamentally changes the electron itself. Okay, here's the best way to picture it. Imagine our electron suddenly has to put on a super heavy, kind of sticky winter coat. That coat, that's the phonon cloud. It's the lattice distortion that the electron is now forced to drag everywhere it goes. And that coat, as you can probably guess, changes everything. A regular, naked electron can zip around with no problem, but an electron bundled up in that heavy coat, which is now a polaron, is way slower. It's harder to get it to move. In physics, we say it has a higher effective mass. It didn't actually gain weight, but it sure acts like it did. So let's just break it down one more time. Step 1. An electron cruises into a crystal. Step 2. Its charge immediately starts messing with the atoms around it, creating that phonon cloud. Step 3. And this is the magic moment, the electron and its cloud basically get stuck together, becoming one single unit. And boom, step 4, you've got yourself a polaron, a dressed-up electron that's heavier and slower than before.
All right, so we've established we have this slower, heavier quasi-particle called a polaron. Cool. But what on earth does that have to do with my window turning dark? Well, it all comes down to how these polarons get around. It turns out they hop.
See, a polaron doesn't flow smoothly. It jumps or hops from one atom to another. But to make that jump, it needs a little kick of energy. And where does it get that energy? It gets it by snatching a photon of light. So if a polaron needs to absorb a red photon to make its jump, guess what? That red light is now gone. It doesn't make it through the glass to your eye, and the color of the material changes. But wait, it gets even cooler. Sometimes two of these polarons actually pair up. They form something called a bipolaron. And when this pair of dressed-up electrons decides to hop together, it's a totally different kind of move. It needs a different amount of energy, which means it absorbs a different color of light. And here is the absolute key to the whole thing. The single polaron hops, they tend to absorb light in the near-infrared spectrum. This stuff we feel as heat. But the bipolaron hops, they need more energy.
So they absorb light in the visible spectrum, the light we can actually see. This is huge. It means by controlling how many single polarons versus bipolarons you have, you can control heat and light separately. That is the secret sauce for a truly smart window.
So, now that we have this unified theory, it's not just about explaining how current smart windows work. No, this is like getting a brand new instruction manual for building the materials of the future.
I mean, listen to what the researchers themselves are saying. This polar model isn't the end of the road. It's the beginning. It gives scientists a blueprint, a roadmap, to start designing brand new materials with whatever optical properties they want. So let's just recap why this is such a game changer. We finally have one single, elegant model that explains this whole class of color-changing materials. We understand exactly how they control both visible light and invisible heat. And most importantly, this knowledge lets scientists stop guessing and start engineering the next generation of smart windows, amazing new displays, and who knows what else. And it really leaves you with a pretty wild thought, doesn't it? The polaron is just one type of these bizarre quasiparticles. If understanding this one hidden interaction inside a material can unlock technology like this, what else is hiding in there? What other seemingly impossible materials are just waiting for us to discover the strange, beautiful physics that makes them tick?